Okay, so far we talk about the BF algorithm or the Bellman-Ford algorithm, and we discussed the time complexity, and that is OVE. And OVE, what does that mean? Well, if I ask you this thing, so for the Bellman-Ford algorithm, how many times do we have to visit each of the edge? How many times do we have to visit each of the edge? So if you come back to this example, and you may say for each of the edges, and say I did the 1AB, right? So the round 1, I visited AB, and then I say I want to do 2AB, 3AB, 4AB. So I have to visit the edge AB for a total of 4 times. So why it is 4? Because 4 is 5 minus 1, and 5 is the number of the vertices. Okay, so this will give us a OVE algorithm, and we really have to visit the edges a lot of times. It is a problem because, well, if I ask you V and E, which one is larger? Well, usually E is larger, right? So we have more edges than the vertices in a gram. So that is bad. We have to visit each of the E for V minus 1 times. So can we do better than that? Well, yes, there is another algorithm called Dijkstras algorithm. And for the Dijkstra, this is the inventor of this algorithm. I think he is a Dutch scientist. Okay. This is definitely a weird name, by the way. For the Dijkstra algorithm, it only works when there is no negative edges. Okay, so before you do the Dijkstra algorithm, first check whether if you have a negative edge or not. Well, the idea of the Dijkstra algorithm is, as I said, I want to reduce the number of visiting the same edge again and again and again. Well, the mindset is a little bit similar to the breadth first search, BFS. Well, we are trying to explore our boundary gradually. So we started from the source. That is the only node we have, and then I want to explore a little bit and explore even more and keep on exploring. Okay, and it also brings some of the idea from the Prim's algorithm, because well, we are going to try to maintain a queue, and we are going to use a a binary heap version of the priority queue again. We are going to see that when we discuss the time complexity. So this is the code of the Dijkstra algorithm, and well, I know this is scary. Well, I don't want to read this kind of code. Well, let me show you what some of the important things first. So the first part, queue. So queue is the unvisited nodes. So we keep that as a set, and then for the S, it is another set, the visited nodes. Okay, and then when you see this phi means it is an empty site. Okay, so the first part we want to do for each of the vertices, and we update the distance, or the shortest path to be a infinity. And after that, we know there is a source. The source is S, so we specify the distance of the source to be 0, because starting from the source, the cost to get to the same source is a 0, right? And then S. So what is S? S is a visited node. So S is a phi saying for the visited node, that is a empty set. And then for the Q, what is the Q? Q is the unvisited node. So for the Q, it is the V. So I'm putting all the vertices into the Q because they are all unvisited nodes for now. And after that, as long as the queue is not empty, so the queue is unvisited nodes, and the goal is in each round we want to take one out from the queue and then put that into the S, and I'm going to keep on doing that until I have already taken all the nodes from the queue and put them into the S. Okay, and then I want to do a extract min. You have seen this before, right? Well, I'm trying to extract the minimum. And after extracting that, I'm merging the U to the S. This means I'm extracting the minimum from the Q, and then and the minimum will be the U. And after that, u has already been taken out from the q, and then I'm putting that into the s. And then for each of the v that I can access using from the u, and then I'm doing this part. And what is this code? What is this code? That is a relaxation, right? So I'm relaxing u, v, and w. Okay, so that's the Dijkstras algorithm, and that still look confusing. I know that, and let's try this on a real example. Okay, so remember we are maintaining the q and the s, and s is the set of the visited node, and q is the set of the unvisited node, and I'm using the d, and that is the distances between the source to each of the node. Okay, so let me work on this example here. So and in this solution, I'm working out this problem from the left side to the right side. And to start from, I know this Q has all the nodes, and then for the S, well, it is empty set. And to begin with, I'm gonna do S infinity, infinity, and infinity, because I'm gonna specify S to be the A. Okay, so I'm starting from the A, so I know from the A I can get to A with the cost of 0. So that's the first one. Okay, and the first thing we want to do a extract mean. So for the A, B, C, D, so this is the D list. Okay, so for the A, B, C, D, which one is the minimum? Well, the minimum is 0, right? Because we have 0 and 3 infinities. So extract the mean will give us the 0. And then from this 0, from this A, so I'm taking the A out, and now A will be A will be moved to the visit set. And then from A, where can we go? We can go A to B, and then the cost is 10. So A to B, the cost is 10. And originally, well, we can go to B with the cost of infinity. So have we found a shorter path? Yes. So I want to update that. And then this is a relaxation, right? I have already found a shorter path from A to B, because originally it was infinity, and now I found a path as a 10. And how about C? It's the same thing. Originally that's infinity, but now I have found a path from the A to C that is 5. And how about D? No, I can't go to D yet. So infinity and it's 0. So now I have already moved the A out. And so remember, I'm making a mark here saying A has already been moved out from the queue. Okay, so if we want to do a extract mean again, remember A is not in the queue anymore, right? So we can only extract the mean from the B, C, and D. And then from the B, C, and D, which is the mean? That is the C, because C is 5. So now I want to go to the C. And then from C, I can go to D with the cost of 1. So C is 5, and add the cost of the C to D, and then it will be the 6. Do we want to relax that? Of course, because originally the cost for going to D is infinity, and now I find a shorter path that the cost is a 6. Okay, and from C I can go to B. So from C to B, that is the cost of the C is 5, and C to B is a 4. So that is a 9. Should I do a relaxation? Yes, because 9 is reduced to 10 is reduced to 9. So that is another relaxation. And for A, C cannot go to A directly. And for C, that is the same 5. So I cross out the C, and then I move that here. So I make another marker saying C has already been visited. So now we only have B and D. So for the B and D, if we want to extract the mean, that will be D. So D is moved down here. So from D, I can go to B. From D to B, the cost is 2, and the cost to get to D is a 6. So 6 plus a 2 here, that will be 8. Do we want to relax? Yes, because we are reducing the cost in getting to B from from 9 to 8. So D can only go to B directly. So I'm going to copy the remaining values. So D has already been moved down. So the only one I'm going to do in the extract mean will be B, because B is the only value now. So I'm moving B down here. And after that, from the B, I can go to C, and the cost is 3. So B is 8. And then 8 plus the cost of the B to C, which is 3. I find another path which I can get to C with the cost of 11. So do I want to relax here? Do I want to apply the relaxation? The answer is no, right? Because we have already found a path from A to C that is the cost is 5. I find a new path, but this path is longer, so I don't want to have that. So no, I'm going to keep the 5. So what else? No, B can only go to the C, and then I'm going to just copy the remaining values. So, ta-da! Surprisingly, it has already been done. Okay, so this is the cool thing about the Dijkstras algorithm. Okay, do you see that? Well, we finish everything in one pass. So remember, when we did the BF algorithm, we finished everything in 4 passes, and I only show you how to do one pass of that. And for Dijkstra, I actually show you the full solution, and this is how we can solve the problem. So is the Dijkstra algorithm faster? Of course, yes, right? Okay, so I'm going to stop my video here, and in the next video we are going to do a further analysis of the Dijkstras algorithm. Okay, so there's only one more video to go, and then we are going to finish today's lecture. I know today's lecture is a long one. Okay, so see you in the next video.